In this video, we will take a look at confidence intervals for proportions. So this will be an introduction to confidence intervals, not the full-scale confidence interval. So really what we're doing is we're beginning to work on inference, which is all about making predictions of the unknown. So if you think weathermen and how they say, or women, how they say there's going to be between this many inches of rain and this many inches of rain or snow. Presidential elections when they have predictions about who will become president and a margin of error of that prediction. So again, we don't know what's going to happen, but these statistics give us a pretty good idea. So this week we're going to look at proportions. So we'll look at confidence intervals and hypothesis testing. Next week we'll deal with means, and then our final week we'll deal with inference based on two samples. So recall from last week that we looked at a sampling distribution model of p hat, and remember p hat was just the predicted proportion, and it was centered at p, which is the population proportion. So remember when we were talking about p hat, this was from our sample, so what we actually observed, so that's real data that we observed, and if you're looking at p, that was from the population. So that's what we expected to happen. And then we talked about having a standard deviation of PQ over N and the square root. However, in the real world, we often don't know P. So we don't go into it knowing, that 53% are going to vote for a certain candidate. So all we can do is look at the data that we actually gather ourselves and then try to make some inferences based on that. So what we're going to do instead of using this standard deviation is we're going to use something called the standard error. And it's called a standard error because it's less precise than the standard deviation. And again, what we're doing here is basically the same process, but notice here I'm using p hat and q hat, which means when I'm finding the standard error, I'm using my sample data. And again, this is for a confidence interval specifically, so we'll talk about how that's different when we're doing a hypothesis test. But again, make sure when we're doing a confidence interval, we don't know what P is. So we have worked quite a bit with the empirical rule. And first of all, we know that the empirical rule is just an estimate. And so notice I'm using about 68%. And again, I'm looking at how many samples, which means how many p hats will be within one standard deviation of p, and how many p hats will be in two standard deviations of p. So if I drew my model, in the middle would be p, and I'm saying 68% of the time p hat will be here within one standard deviation. But here's the problem. We don't know what p is quite often. And so instead, we can't center our model at p. We have to start with p hat in the middle, which makes things a little bit less precise. So consider a 95% level based on the empirical rule. When p was in the center, we found approximately 95% of the time our sample, which is p hat, was within two standard deviations of p. Now that we're going to have p hat in the center, if we reach out to standard errors, so now we're not using standard deviation but standard error, which remember was p hat q hat over n, all based on our sample, then we're 95% confident that we're capturing p. So we're 95% confident that p is going to be in this range. So if I drew my model now, p hat's here in the middle, and I'm saying, okay, two standard errors to each side, I'm 95% confident that the true p is in there somewhere. I could be wrong, it could be outside of that, but I'm 95% confident that it's in there. This is called a confidence interval. So a confidence interval is centered at p hat, which is our observed value, and what we're trying to do is trying to hypothesize what the actual p-value is. So essentially, a confidence interval is just a range of values that we believe contains the true population parameter. When I say population parameter, again, I'm just talking about P. So, and it's centered at our observed proportion, which means that's where I'm talking about P hat. So each confidence interval uses a sample statistic. So if I created a confidence interval, it would be based on my sample. And if you created a confidence interval, it would be based on your sample. So while our two confidence intervals would be different, we would both be, 95% certain that we captured the true value. And obviously those numbers in our ranges would be different than one another, but that doesn't mean that we're wrong. We're still 95% confident that we have captured the true value because, of course, we're assuming there's going to be some overlap. So think of it this way. If this is my p hat, then I've got my normal model here. Let's say your p hat happened here. We'll just put a sub 2. Which means your 95% interval looks like this. And so if I'm looking here at 95%, and then you're looking from here to here, I'm looking from here to here, we're still 95% confident that somewhere between those values is the true value. So maybe it's right here between our two. Again, we don't know. This picture is a much better representation than my chicken scratch on the last slide, but this is essentially saying that if the green line is the actual P, and remember P is unknown, but let's say that is the actual P value. Notice this is several 95% intervals, and on my first interval we can see that I did not capture the true proportion because all of my data is outside of P. But on my second one I did, and on my third one I did because it crosses the green, and fourth I did, and fifth I did, sixth I didn't, seventh I did, eighth I did, ninth, 10th, 11th, 12th, not the 13th, 14th, 15th, 16th, 17th, 18th, 19th, and 20. So 17 out of 20 times I did capture the true P. Again, it's not an exact science, but what we're saying is if you do everything right, if you collect your sample correctly, and we've already talked about how to collect a sample correctly to remove bias, if I do all of those things and I follow the rules for proportions, I'm 95% confident that I'm going to capture the true proportion of P. So before we actually create a true confidence interval, I just want to give you an idea of where we're headed or what we're looking at. So let's say a recent survey found that 52 of 148 Facebook users update their status daily. So the first thing I would look at is this a means question or a proportions question? Now this one did not give me a percentage, but it did give me 52 out of 148, which I can use to calculate p hat. So about 35.14% update their status daily. So that means if I'm drawing my model, right here in the middle is 0.3514. Now what I'm going to do is I'm going to calculate the standard error, and again, not as precise as the standard deviation, but I don't know the true percent of people who update their status daily. I just know based on 148 how many did. So I'm going to use my formula that says standard error is p hat q hat over n, and I've just calculated p hat. Remember, q hat would just be 1 minus p hat, so 1 minus 0.3514, and that's where I came up with 0.6486. And so to find my standard error, I'm taking p hat q hat divided by n just being the number, the size of my sample, which is 148. And essentially what I've done then is said, okay, if this is my standard error, I'm just going to count over two of them to the right. So I'm adding two standard errors to 0.3514 to get 0.4298. And I'm subtracting two of them to go to the left, 0.273, and essentially what I'm saying is I have found 35.14% of Facebook users update their status daily, but that was based on a sample of 148. So I'm 95% confident, and again, we're going to be more precise in a little bit, but I'm 95% confident that between 27.3% and 42.98 or 43% of users update their status daily. So I'm using my sample of 0.3514 to say that the true proportion of users is somewhere between 27.3 and 43%. Again, what does that tell us? First of all, this is how we would write that in interval notation. And an interval notation, in case you don't recall from previous math classes, is an interval that goes from least to greatest. And the interval says that we're looking at all of the numbers between 27.3 and 42.98. So that's my confidence interval. Now, what can I say based on that? That I don't know the percent of Facebook users that update their status daily, but I'm 95% confident that it's between those two percentages. Or, as I said on the previous slide, I'm 95% confident that between 27.3 and 43% of all Facebook users update their status daily. I cannot say that 35.14% of all Facebook users update their status, because that was based on one sample of less than 200 people. So clearly I'm not going to do that. And I also can't say that I'm certain that it will fall in this interval, because there's always room for error, and we'll talk about error more in a little while. But again, I can't say I'm sure it's there. I can only say I'm 95% confident that it's between those two values. Again, as we work through this week and the next 2 weeks of material, we're going to be learning about a lot of different intervals and tests, etc. And it's going to be important that you keep straight which is which, because eventually I will ask you some matching questions as to what's the most appropriate for each situation. So this is called a one proportion Z interval. So it's one proportion because obviously we're dealing with a proportion and there's only one of them, which I'm going to show you how to deal with two in a couple of weeks. And it's a Z interval because we're dealing with a normal model.